Okay. Maybe we can wait 1 more minute because it seems that people are still having lunch.
Mm-hmm.
Yes, there was a delay in room A before the lunch, so we have finished half an hour later because there was a long discussion. The first two talks of Martin Lindsay and Tom Goff, they were longer than expected, and then okay. So the third talk has started, I would say, around 20 or 25 minutes later, and then half of lunch was eaten by the session. Oh, I don't know. Or there are a strong competition. There are 3 rooms, so probably some other people already exhausted with the 4th day of the conference. Who knows? There are somewhere very nice birds. Delio, is it your birds?
Yeah, it's my parakeets. Can you hear them?
Yeah.
Okay, then I will have to shut the micro during the talk. Yeah, they're very loud in the early afternoon, that's true.
It's what kind of birds they are?
Parakeets, so like small parrots.
Okay.
It's wellensittich in German.
I don't know how to say it in German. Okay. Only in Russian. Волнистые попугайчики. So Damir can translate, probably it is the same or not. No idea.
Okay, I think we can start, otherwise we have a problem with the schedule.
Yeah.
Okay, so
Sure.
we're invited to this afternoon session in room B. And I'm very glad to introduce Damir Kinzebulatov. I'm sorry, I was certainly pronounced your name wrong. Who's going to talk about fractional Kolmogorov operators. So please go ahead.
Thank you very much. Thank you to the organizers and to Yana Budko in particular for the opportunity to speak here. I will be talking about joint results with Yulia Semyonov from Toronto and Karol Szybkowski from Wrocław. All right. Right here. Here's the fractional Kolmogorov operator. We'll be working in dimension greater or equal to 3. So this is a fractional Laplacian perturbed by a drift term. The vector field B has it's defined here. It's a Hardy type vector field. It has a critical singularity of the origin. What does it mean is that in general, when we consider, well, when we're discussing the perturbation of, say, fractional Laplacian, it's assumed that the perturbation is somehow subordinate to the unperturbed operator, the fractional Laplacian. But here, the singularity of the vector field is such that the drift term is roughly equal in strength to the unperturbed operator, the fractional Laplacian. This is going to affect dramatically the properties of the operator. That is, we will see that the heat kernel of this fractional Kolmogorov operator will look nothing like the heat kernel of the unperturbed operator, the fractional Laplacian. So, but let me say a few words first about the probabilistic aspects of this object. So here's the corresponding stochastic differential equation. So the fractional Laplacian corresponds to the alpha stable process. So what we are having here is the alpha stable process perturbed by a drift. So the second term, the integral, and as you can see, the coefficient in front of it, the coefficient kappa, which is assumed to be positive, the effect that it has on the process is that it enforces a certain repulsion from the origin. So as I mentioned, the subject of this talk are two-sided bonds on the heat kernel of the Kalmagorov operator that has this probabilistic interpretation. And once again, the singularity of the Hardy vector field, evidently it explodes at the origin. So the singularity is so strong that it will affect the heat kernel bonds. Namely, we will see that what happens to the heat kernel bonds is that there will be an extra weight that vanishes at the origin. And the rate of vanishing will be determined by the coefficient kappa. So the properties of the operator will be sensitive to the scalar multiple of the vector field. But right now, let me take a step back and talk in general about this general program of studying critical singularities or singular vector fields. Of course, this is a classical and one of the central questions in the theory of PDEs: what singularities, what coefficients are admissible? And more precisely, what is the relationship between the integral characteristics of the coefficients, like the vector field F here, and the regularity properties of the solutions? By the regularity properties of solutions or regularity properties of the equations, we can be more precise. For instance, existence and uniqueness of weak solutions to the corresponding stochastic differential equation, bounds on the heat kernel, and so on. We will see that if I can go back to the slide, we will see that the value of this coefficient kappa in the vector field B is extremely important and really affects even the solvability of the corresponding stochastic differential equation. All right, but so I took a step back and I'm talking about the existing results. There is one class of vector fields that plays a prominent role, namely the Kato class. So a vector field is assumed to be locally in L1, and one adds the following condition that expresses the assumption that the vector field is somehow small with respect to, or rather the drift term is somehow small with respect to the unperturbed operator, the fractional Laplacian. This class of vector fields contains the class that can be expressed in terms of LP conditions on the drift. P is strictly greater than D divided by alpha minus 1. This exponent is optimal. One cannot go beyond that on the scale of LP spaces. But at the same time, one shouldn't stay in the scale of LP spaces, as this class suggests, because there are vector fields in the Kato class that are not even locally in L1 plus epsilon for any positive epsilon. Right. Okay. Now, if the vector field belongs to the Kato class, so its role of the Kato class in the context of the fractional Laplacian was recognized in the fundamental paper of Bogdan and Yakubovsky, who have established that under this Kato class assumption, even if vector field, say locally in L1, or there are vector fields that are locally in L1, not even locally in L1 plus epsilon, nevertheless, without any extra assumptions of the drift, such as regularity of the divergence, nevertheless, the heat kernel of the Kalmagorov operator is equivalent, well, there is the precise meaning, to the heat kernel of the fractional Laplace operator. Here, when I say heat kernel or fundamental solution, but it will be defined as the integral kernel of the corresponding semigroup. Now, and in the like stochastic setting, this Kato class was studied in the papers, in the works of Chen, Funky Kim, Rin Min Song, and others. Now, the question that, I would like to emphasize once again that the Kato class is essentially the class of vector fields that provides this equivalence of the hit kernel of the perturbed operator and the hit kernel of the unperturbed operator, the fractional Laplacian. Now, the question that I would like to address in this talk is: does life exist beyond the Kato class? Can one go beyond the Kato class and still have a sharp, that is two-sided, hit kernel bounds for vector fields that are not in the Kato class, such as the Hardy drift? Now, I'm not the first one to ask this question. In fact, it was studied already. So does life exist beyond the Kato class? In the local case, Schrödinger operator, the answer was obtained in the paper of Milman and Semyonov. In the fractional case,
the question is positive or negative?
Positive or negative. Does life exist?
Yeah,
so you mean the answer, whether the answer is yes or no?
Yeah, in the examples.
The answer is yes.
Okay.
In the symmetric case, so the Schrödinger operator potential, the answer was obtained by Milman and Semyonov, who established sharp two-sided bounds on the hit kernel with a weight. In the fractional case, the case of the negative potential, Milman and Semyonov actually considered both cases, positive and negative potential, and the distinction is important here. In the case of the negative potential, your extra weight explodes at the origin. In the case of the positive potential, it vanishes at the origin. So it forces your fundamental solution of the hit kernel to vanish and stay there and stay there. All right. So in the fractional case, of the negative potential, the result was corresponding result was obtained by Bogdan, Grivny, Kubovsky, and Pilarchik. And of course, the fractional case is quite different, or very different. I will explain that. In the case of the positive potential, Cho Kim, Song, Rin Song, and Zoran Vondrachik, Tomasz Kubovsky, and Zheng Wong obtained the corresponding result at the same time. In the non-symmetric local case, that is the drift perturbation, which complicates things considerably if you compare it to the potential perturbation by potential. The corresponding result was obtained by Giorgio Mitafune, Negra, Sabajima, and Chiara Spina. And in fact, they considered general second and zeroth order perturbation. So Hardy potential plus a matrix that sort of an analog of the Hardy drift and Hardy potential. Finally, non-symmetric non-local case. That's the subject of this talk. In the case when the drift is sort of positive, or we should talk about the sign of the divergence, the corresponding result was obtained in the paper of Semyonov, Shukovsky, and myself. And in this talk, I will talk about the different sign, the opposite sign. So this talk will focus on the opposite sign. So in this paper from 2019, what one observes is the effect of the attraction. Here's the repulsion, which, well, requires new ideas and new methods. In particular, we will use the method of self-improving estimates of Kubovsky and Wong, in addition to the method developed in this 2019 paper, plus some new ideas. Okay, let me state main result roughly, ignoring for a moment how we construct the hit kernel for this operator. This is an important question because the standard techniques do not apply. I will explain it in a moment. But assuming that we have the hit kernel, here's the result. Its hit kernel is equivalent, so there are two-sided bounds to the hit kernel of the fractional Laplacian that one can estimate explicitly. There is a very nice estimate, times a weight that vanishes, and the rate of vanishing is determined. So the rate of vanishing beta is determined by the coefficient kappa. This weight psi is bounded. It's continuous and bounded. It's not smooth, but continuous and bounded, and which shows that the standard upper bound in terms of the fractional Laplacian is still valid in this case, but it's off the mark. It's suboptimal because the heat kernel actually vanishes, while the lower bound is simply invalid. The lower bound in terms of the fractional Laplacian. So I should say that I have 37 slides because I included some technical details in case there are questions, but of course it won't take that much time. Okay, so let me say a few words about the proof. The semi-group that we will construct is ultra-contractive. So the upper bound exists, but it's better than ultra-contractive. It will stay ultra-contractive even if we sort of embed it into a weighted space with a vanishing weight psi. So that's the idea behind the desingularization method introduced by Milman and Semyonov for Schrödinger operator. I mentioned the result a few slides before. Right, and so we will use the desingularization method. Yeah, I will explain in a moment that unfortunately the techniques, the actual details of how it works, in the paper of Milman and Semyonov, it won't work here because we have a drifter and the fractional Laplacian. It affects the techniques that are available. Just a few words about the proof. Actually, the proof, I will concentrate in this talk on the proof of the upper bound. As you can see, there is no, so the so-called Nash initial estimate with the weight. And as you can see, the heat kernel with fractional Laplacian is replaced by the corresponding on-diagonal bound. Then we will, what happens is we prove the standard upper bound that is still valid. And now what's left is the task to combine these two bounds, which is will be done using the method of Jakubowski and Wong. But what we have here, these two estimates are not enough to apply their method directly because we don't have any control of the constant C. It has to be close to 1 in order to ensure that the geometric series converges. So what we'll do is we will refine the standard upper bound, but only for some values of x and y. And this will be enough to apply their method of Tomasz Jakubowski and John Wong. But in this talk, I will concentrate on the first step. And this is where the desingularization happens. Okay, so let me talk about the construction of the heat kernel, the construction of the semi-group. If the coefficient in front of the vector field, and it's written on top of the page, if the coefficient is sufficiently small, which would be a rather unreasonable assumption, then the construction of the semi-group is easy. It's simply the algebraic sum. This is no longer a formal operator. This is an algebraic sum on the domain of the fractional Laplacian. We defined explicitly. We can simply guess what the Neumann series must be, and so no problem at all. The problem is that this kappa, so it corresponds to the repulsion. So the larger kappa is, the better the properties of the semi-group should be in some sense. But this is not visible in this approach because one has to ensure the convergence of the geometric series, and this won't work. So the form method, it will not work because the gradient is stronger than half of the unperturbed operator. It's simply not clear how to even start, where to begin. So as you can see, the problem of constructing the semi-group, even in some space in L2, becomes non-trivial. So what we will do instead, we will use a direct approximation argument. We will consider approximating vector fields. So we smoothed out drift. We will consider the corresponding smoothed out, well, the corresponding operators. And what we do is we prove that the limit of the approximating semi-groups exists in LP and LR for R between 1 and infinity. It exists, and its limit is a strongly continuous semi-group, positivity preserving contraction that satisfies this RQ estimate. The generator of the semi-group is the operator realization of the formal operator lambda that we have on top of this slide. So this operator will be constructed as the generator of the corresponding semi-group. Now, to show the convergence of the approximating semi-group, well, we can do something very straightforward. We can take the difference between, well, two solutions of the corresponding parabolic equation and show that this difference is a Cauchy sequence. So I mean, we want to show that this approximating solutions is a Cauchy sequence. So we take the difference, we find the equation satisfied by this difference G, but this is an equation in quotation marks, because while it's nice, there is this extra term, the fourth term on the left, that contains not the difference G, but actually the gradient of the solution. But fortunately, we can control, or rather, I should say that it's well known that if one has a strong regularity estimates, then it helps. And here we will prove a regularity estimate on the gradient written below, which will allow us to show the convergence of that really the approximating solutions constitute a Cauchy sequence. So the question is, how do we obtain this estimate on the gradient? And so I've stated the corresponding result here. Let me just say that this inequalities for Markov symmetric Markov generators, they allow you to do the calculations for symmetric Markov generator like the fractional Laplacian as if it was a Laplacian, losing some with some loss. So for Laplacian, you would have equality rather than inequality. But these inequalities we used previously to study the solutions. And as far as I know, this is the first time that these inequalities, or rather the vector valued analogs proved in this work, I used to study the gradient of the solution. So we do that, we obtain that a priori bound on the gradient of the solution, we show the convergence, and then the Dunford theorem and LPQ estimate on the semigroup plus Dunford's theorem yield that this is a semigroup of integral operators. Its integral kernel is the hit kernel of the operator lambda. Now, as far as I understand, I have a few minutes.
You have 10 more minutes.
Oh, thanks. The problem is that my teaching starts in 10 minutes. Okay, okay. So the second part, the proof of the Nash initial estimate. So the upper bound on the hit kernel with the weight and sort of on diagonal component. Okay, here's the precise definition of the weight psi s. As you can see, this well, it's essentially, it has this polynomial behavior at the origin, t to the power beta. Outside of the ball, certain ball, it's just a constant, and this beta is determined from the very first equation. That involves dimension, obviously, alpha, the power of the fraction Laplacian, and kappa, the coefficient of the vector field. So one can show that kappa actually determines beta uniquely. That's the graph here. So with this choice of beta, the function, the norm of x to the power beta, is Lyapunov's function of the formal adjoint operator. So this is where it comes from. Basically, we will need this equality, but not at the formal level, but something much more concrete. All right. So the weighted Nash initial estimate, I will already mentioned it a few times. So this is the precise statement, or just a reminder of what I want to prove. Now, the abstract non-symmetric desingularization repulsion case. Well, there is this abstract result that we will apply, that we prove and apply. So there are a few conditions. The ones that are in red or in brown, although they're scary looking, but they will be satisfied by the weight quite nature. It's basically some scaling conditions. So let me just say that. The principal condition is are the ones in blue. The Sobolev embedding property, again, it will be, it's relatively easy to show, rather easy to show. The principal condition is this L1 bound. L1 bound that will force us to embed our semigroup in the weighted space. But here I'm talking about just abstract setting. We assume that we have a semigroup in some space that satisfies this L1 bound. hold on a sec. No, I'm actually, that's not what I wanted to say at all. So this is, we have this L1 bound that will be satisfied by our semi-group easily. Again, nothing to worry about here. The principal bound is this bound star. So we consider weighted semi-group, and it has to satisfy the L1 bound stated in blue. If one has that, then an argument essentially following the proof of the non-diagonal bound by Nash gives you the required estimate, the Nash initial estimate. This focus on the L1 bound is really specific to the method of Nash, and basically we will follow the general philosophy of the method of Nash. Now, to prove this L1 bound is, well, that's where the main difficulty is. Now, let me say a few words about what happens with the Schrödinger operator. For the Schrödinger operator, one can formally do the following calculation. So let's consider the weighted semi-group. It's basically the weighted operator, psi s, lambda psi s inverse will be the generator of the weighted semi-group. It's not, at least in the weighted L2 space, it's relatively easy to see. Or rather easy to see, but on the other hand, this weighted generator can be calculated explicitly. One gets these extra terms that will kill the singularity of the potential. So the weighted operator is actually one still gets an operator with singular coefficients because there is this gradient term, but this is enough to obtain the L1 bound. This is what Milman and Semyonov did. They, of course, to make all the operations, to justify all the manipulations with the equation, they had to work, and one has to work with smooth approximations of the potential and smooth approximations of the weight. It should be psi s, not phi s. The problem is that for the fractional Laplacian, the calculational and approximation techniques are simply unavailable. The moment one uses this or rather straightforward approximation of the weight using the modifier, then one loses the possibility to do the calculations. One can do calculations at the formal level with this Hardy type vector field because somehow it matches the structure of the fractional Laplacian, but when you smooth it out, everything becomes much more complicated. So I'm almost done. Let me just state, I won't be talking about the details of the proof, this detailed calculations, but I will, nevertheless, I want to mention the main idea. So we will prove this L1 bound, the key to the Nash method, for the smoothed out operators lambda epsilon and for the smoothed out weights. There are two parameters here, n and epsilon. So the smoothed out operators, smoothed out coefficients defined as usual. And as for the, skip that. And as for the smoothed out weights, here's the definition of the weight. The principal idea is that, or rather, sort of the novelty is that we, as a modifier, we define the modifier in terms of the smoothed out operator, rather than taking something standard. With modifier defined in this way, one can basically commute in the calculations. One can commute this modifier with the operator, and this is really the key that allows to arrive to the result. Basically, the last sentence would be here that we prove this L1 bound, and once again it's stated on top, by showing that the corresponding operator is accretive in L1. And yeah, and we do it thanks to this carefully chosen approximation of the weights. That's it. Thank you very much.
Thank you very much for your talk. Other questions?
Well, do you have a few minutes, Damir, or you have to vanish immediately?
I have a minute. My teaching starts.
Yeah. Then I have no questions. I guess it's not that important.
good. Thanks.
Maybe just a very short question myself. So do you know anything about your function psi? So you have this lower bound by the classical heat kernel times psi t.
Right.
Does it suggest something about positivity?
About what?
Positivity.
About positivity. Well, yes, of course, it will be positive because we also have the lower bound, which is once again the heat kernel of the fractional Laplacian times this function psi, and psi is defined explicitly here. So psi is this new function eta. Yeah, and it's,
so it
is
a positive function.
Yes.
Okay, this was my question. And is it a Markovian semigroup?
Oh yes, of course, yes. Yeah.
Okay.
It will be more. Yeah.
Okay, thanks.
We can actually solve stochastic differential equations for this drift and for much larger class of drifts, actually. Now, this will be the talk of Rafael Madou in half an hour.
Okay, thank you.
So thank you. Have a nice teaching.
Thank you. Thanks once again.
Okay, if there are no further questions, then thank you again. And we have a couple of minutes break.
Yeah, it's quite strange that the second speaker is not here.
I think
he's here. So he's here.
Yeah. I saw him before. Maybe we can try those slides.
Okay, can you see?
Yeah.
Yes.
Yeah, seemingly this section is now not too popular. Probably there is a big competition, a hard competition.
And my experience after a couple of months or maybe 1 year in pandemic is that the first 1.5 to 2 days are very popular, and then attention diminishes a bit.
Yes. So I was trying to follow more or less all the talks, and then I realized that after half of the day, I'm just not able to focus on what's going on. And yeah, so probably some people are already exhausted. So probably we had to make the lunch 2 hours to make people really refreshed, but who knows? Next time.
Or maybe